Hello everyone, I hope everyone is doing well. In this particular week, we will be covering public key cryptography, Diffie-Hellman key exchange, discrete logarithmic problem, knapsack cryptosystem, RSA algorithm, El-Jamal encryption algorithm, and if time permits, elliptic curve based cryptography. So let's first talk about the problem with the symmetric key cryptography algorithms that we have discussed so far. So before I jump into it, let's talk about the basic functionality that is required for any kind of, or I would say the basic fundamental objective of cryptography is, let me share my whiteboard one second. Okay, so let's suppose there are two parties, which is Alice and Bob. The main intent of a cryptographic system is that Alice and Bob can communicate with each other in an insecure on an insecure channel, such that if an attacker tries to eavesdrop the information, he or she would not be able to identify what is that information which is being exchanged. This particular, so the main intent over here is to communicate over an insecure channel such that the information is still secure. So the way symmetric key cryptography works is that both Alice and Bob can communicate through a single key over here, which is known as a secret key or a shared key. And this secret key and the shared key has to be known in prior so that they can communicate with each other. So Alice can apply an encryption algorithm using the key K on the message so that it creates the ciphertext. Bob and this ciphertext is communicated on this insecure channel. Bob, on receiving this ciphertext, can apply a decryption key, which is D over here, on let me just write decryption key using the key over here, which is D, on the ciphertext in order to generate the message M over here. So here both decryption key and the encryption key, in an asymmetric key cryptography, it could be the same or slightly it's shared among each other, or it can be generated using one or the other. This is what was termed in an asymmetric key cryptography algorithms. Here encryption algorithm could be of various type. It could be block cipher, it could be AES, it could be DES, and we discussed about all of these algorithms where the key bit could be 128 bit long or 256 bit, and it depends upon the algorithm that we are using. Similarly, we used a key stream generator where a key stream can generate keys K1, K2 to Ki, and if we have a message M1, M2 to Mi, the algorithm, or I would say the output of this would be the XOR of M1 and K1, M2 and K2, and this is normally works with any kind of, I would say, asymmetric key cryptography algorithm. But what is the problem with this kind of symmetric key cryptography algorithm? So the problem with this symmetric key cryptography algorithm are two ways. One is that how do we communicate the secret key between the two? If we communicate the secret key on the insecure channel, somebody can listen in that particular key. Let's suppose that Alice wants to say that I want to use this particular key with the communication. So if Alice wants to use that particular key with the Bob, they have to communicate it. And let's suppose Alice calls Bob, yes, I want to use this key, but that particular key becomes now vulnerable. Anybody can listen in that key, and we know that. So that's one of the major problem, and for this Diffie-Hellman key was used, and I'll talk about Diffie-Hellman key. And if you recall, in my last lecture I talked about, when I was talking about this federated learning architecture where we secure the model, and normally we can use Diffie-Hellman. So I'll talk about it. One problem is that. The other problem that we have is, let's just suppose if we have 5 people. Let's suppose we have Alice, we have Bob, we have Park, we have Thomas, and we have Jack. And all of them wants to communicate with each other. So for a symmetric key cryptographic algorithm, so each one of them would be having a separate key for their communication channel. So this would be K1, K2, K3, K4, K5, K6, and so on. So in order for all of them to communicate with each other, there would be NC2 combinations that they have to generate, those many keys, which is equals to n into n minus 1 divided by 2, where n is the number of people in that particular group. So this is another problem, that you have to save those many keys. So how we can get rid of this particular problem so that the key is like safely, I would say, exchange between the two, or we can have a different key, which could be using this public key cryptography algorithm, which is PKI, where we have two keys, one for encryption, one for decryption. And that's I'll tell you what was the reason why we chose this particular problem, and that these are the two problems. But before that, let's talk about how these keys can be generated between the two parties without even knowing how it would be generated. So Diffie-Hellman algorithm works in such a way that in the end we receive a secret key between the two parties, but they do not share the secret key, but instead they share something else which is common to each other. So let's suppose that Alice and Bob chooses a common color, which is yellow, and Alice has its own secret paint, which is orange, and Bob has its own secret paint, which is turquoise or teal blue color. They mix these two colors. So both Alice and Bob calls each other and says, yes, let's agree on this yellow color that has to be we would be using for generation of our key. But they won't be sharing the secret color. So Alice has its secret color as orange, and Bob has its secret color as the turquoise blue color. So at the both end, they would be adding these two colors. So this would generate something like yellowish mustard color, and this is generating some form of blue color. Then they transmit this Bob sends this blue color to Alice, and Alice sends this yellowish mustard color to Bob. And assuming that we cannot separate these two colors, we cannot do that. Once on receiving this, Alice can apply the secret color which he had, which was orange in color, by receiving this blue color. And similarly, this this mustard color, he would apply this teal blue color in order to generate this common secret, which would be considered as the key. So this is the common key that they would be using. This is how Diffie-Hellman key exchange protocol works in terms of, I'm just giving you a random real life changes that this can happen, and we can generate a common key over here. So the end output over here is the same result they would be getting. But now let's talk about with respect to some maths over here, and then I'll give you a understanding, or I would talk about how you can generate it. So let me open my whiteboard. Okay, so now let's suppose that we have Alice again and we have Bob. So in Diffie-Hellman key exchange protocol, what they do is that they agree on two numbers over here. One is P and one is G. What is P? P is a relatively very large prime number. So I can write that P is a prime number, and ZP star is a cyclic group. And remember a cyclic group, what was a cyclic group? Cyclic group was any ZP minus 0 such that it is able to generate its own number. Like let us suppose, if you don't recall, let's suppose I have Z6. Z6 could be any number which is 0, 1, 2, 5 over here, which is, as I said, ZP is any number which could be from 1 to P minus 1 over here, which is ZP star. So Z6 could be any number which is 0 to 5. And if I have to apply any kind of operation, so let's suppose if I do 4 plus 5, 4 plus 5 is 9, 9 modulus 6 gives me the value which is 3. 3 is present in this particular cyclic group, which is Z6 over here. And if I generate a table with respect to 0, 1, 2, 3, 4, 5, and similarly 0, 1, 2, 3, 4, 5, and then if I add, so it would be 0, 1, 2, 3, 4 and 5. If I add 1 plus 0, which is 1 over here, 1 plus 1 which is 2, 2 plus 1 which is 3, then 4, then 5, and then 0. Let's suppose this is 3 plus 0 is 3, sorry, this is 2, then again it is 3, 4, 5. 4 plus 2 it gives you 6. 6 modulus 6 gives you 0. And similarly this is 1. So all the numbers are being generated. This is what it was, a cyclic group, if you do not recall that. So ZP star is a cyclic group over here, where ZP minus 0, it will include all the numbers which is between 1 to p minus 1. Okay, so here Alice and Bob, once they agree upon these two numbers, which is p and g, Alice and Bob. Now once they have agreed on this particular number, what they do is, now Alice comes up with the secret value which is a, and Bob has a secret value which is b over here. Alice, once he knows this particular number which is a, what he will do, he will calculate g to the power of a. G to the power of a is the generator. Since it is a cyclic group, so g multiplied a times would be giving you the generator value over here. So g to the power of a modulus p, Alice would be calculating. Similarly, Bob on the other end would be calculating g to the power of b modulus p. Let's suppose that this is equivalent to a, g to the power of a modulus p, and Bob calculates g to the power of b modulus p, which is the value equals to b over here. Now Alice would be sending, so this is the coloring thing. If you recall, we mixed those two colors, and that's what they did. This is a secret color which was yellow, and this is the turquoise blue color. And since p and g was known to each other, so p and g was the common color that they had agreed upon. That was one vibrant color, and this calculates a and this calculates b, if you recall that particular example. So now Alice would be sending a to the Bob, and Bob would be sending b to Alice. Okay, so Alice once computes this, send this to Bob, and Bob once sends this to b. Now once they receive these respective color, what would this Alice would do? Alice would do b to the power of a, because he knows this a, b to the power of a modulus p. Similarly, Bob would do a to the power of b modulus p, because Bob knows b and Alice knows a. So b, if you recall, b's values is equals to g to the power of b mod p to the power of a mod p. So this would be equivalent to g to the power of ab modulus p. This would happen at the Alice side. Similarly, on the Bob side, it would be a's value is g to the power of a modulus p. So g to the power of ab modulus p. So both of the party ends up getting this secret key, which is over here, which is equivalent to g to the power of ab modulus p. This is the example. This is basically what is known as Diffie-Hellman key protocol over here. So even though they have shared g and b, the attacker would not be able to know what is the value of, I would say, what is the value of the key over here, because Alice knows a and Bob knows b. Nobody else knows these secret values, so the attacker would not be able to identify. So this was the Diffie-Hellman key exchange protocol. Let me give you one example so that you understand this. So let's suppose, as I was saying, that in order to have this kind of algorithm, they agree upon the two numbers, which is p and g. So this was Alice and this was Bob. So Alice and Bob agrees upon the numbers which is p and g. P, let us suppose, is 17 in Diffie-Hellman key exchange protocol, it is quite long, which is 2048 bits. So let's suppose I'm just giving you p is equals to 17 and g is equals to 4. And let's suppose that A agrees on the secret number, which is 3 over here, and B agrees on a secret number, which is 6. But 17 and 14 are the two numbers which are common to each other. Now next, as I said, A is being calculated. A was g to the power of A modulus P. So this is equals to 4 to the power of 3 modulus P. So if you will do this, 4 to the power of 3 gives you 64. 64 modulus 17, because p value is 17. So if you will do this, this value would be equal to 13. So now this value, once it has been calculated, this would be sent to Bob. So 13 would be sent, which is the value of A. So which is A is equals to 13. Similarly, Bob would be computing B, which is G to the power of B modulus P. G is equals to 4, 4 to the power of 6 modulus 17. So this value 4 to the power of 6 is 4096 modulus 17. If you will do this, the remainder value that you would be getting is 16. So now once they Bob calculates this B, that would be sent to Alice. So Bob's value is 16, that is sent to Alice. Once they receive this number, as you recall, I had said that they would be doing that particular number. So Alice would be doing B to the power of A modulus P, which is equals to 16 to the power of A, which is 3 modulus 17. This they would be doing. And similarly, Bob would be doing Alice number, which was number 13 raised to the power of 6 modulus 17. Okay, so if you will do this particular calculation, A to the power of B modulus 17, this would be 4 to the number would be 4826809 modulus 17. If you will do, this is equivalent to 16. And similarly, this particular number, if you will calculate, 16 to the power of 3 is 4096 modulus 17. This would give you 16. So in the end, we would be getting the same number over here, which is equivalent to 16, and that would be the secret key over here. So this is a very good, I would say, algorithm, so that you can share a common key between the two parties without actually sending the key itself, but you are using this algorithm to calculate this value. So now, but the problem is with this Diffie-Hellman key exchange protocol is this I have already explained, so all this is good. There is this problem called discrete logarithmic problem. So discrete logarithmic problem says is that when Alice and Bob wants to transmit this information, recall that they would be sending P and G, which is the prime number, and this G. So we can say that this is ZP star, and the generator over here, let's suppose that the generator is A over here. So if the attacker tries to attackers knows this P and G, and if they even because Bob is sending Alice and Bob, they are sending the value of, this is sending B and this is known as A. So on the common channel, you know that the attacker has the access of A and P and G. So what the attacker can do is, the attacker since it would be doing A to the power of this number, which is A to the power A is equals to G to the power of A modulus P. What attacker can do is can change the value of A, and A, we know that A would be any value which is between 0 to P minus 1. If you remember that A value that they choose, Alice chooses a value which is between 0 to P minus 1, and Bob chooses a value B which is less than P minus 1 and greater than 0. So what the attacker can do by using brute force algorithm, can change the value of A until and unless they get that particular number itself. So they can know the key over here, and that is what is termed as the discrete logarithmic problem, that they would be able to identify this value of A, which was the secret just between the Alice, given that they know A and they know P and G. So that was the problem which was associated with this Diffie-Hellman key protocol. That's the reason we came up with public key cryptography algorithm, where we do not agree on a single key, but we have two separate keys. So if you recall, in my initial classes, we discussed about this asymmetric key cryptographic algorithm, where Alice and Bob, if they want to communicate with each other, so let us suppose that Alice wants to communicate with the Bob. Bob would be having its private key and a public key. And what they would be doing, Alice, if we want to, Bob would be keeping the private key with itself with himself, and would be sending the public key. So Alice knows this particular public key, would be encrypting the message that he wants to communicate with the Bob using this public key, and Bob, on receiving this public key, can decrypt it using its own private key over here. And this works well in that particular case because private key is just known to Bob, and anyone who wants to communicate with Bob, they can use the public key associated with it. And that is basically give rise to the, I would say, a public key cryptographic algorithms.